Hey, John here. Let's talk about how to subtract binary numbers. Quick review, we already know how to add them. We already know what 2's complement numbers are, how they're represented, and we know how to calculate the negative value of any given 2's complement integer. In other words, if you're giving me some number x, I can apply the 2's complement rule and calculate negative x, okay? So what then does it mean to subtract two numbers? Well, I want to take an arbitrary thing, -4 minus 8, right? And I'd like to get -12, right? Well, I can observe that that is the exact same thing as saying -4 plus -8. And then getting -12 that way, right? Well, yes, I suppose if this was an episode of Star Trek, this might be considered a bit of a Kobayashi Maru type of move, right? Well, it turns out this is a nice way to do it. Let's not worry about subtraction. I don't want to figure out how to do borrowing and all this other stuff like we did in grade school. Let's just throw that away. We know how to calculate the negative value of something, so let's not waste our time with it. We already know how to add. We know how to calculate negative values. Let's just do the obvious thing and only use adding, okay? We'll come back to this observation in a minute, okay? So what do we need to do? If I want to calculate, in this case, -4, and I want to subtract 8, well, that's the same thing as -4 plus -8. So first thing I need to do is calculate the 1's complement of -8, and then I need to add 1 to that in order to get to the 2's complement. Then I need to add that lot to the -4. All right, now let's come back to this comment right here. Since we always have a carry in of 0 over here, except now, look what I've done here. In all prior examples in your entire life, right, whenever you add longhand, you never have a carry that comes into the least significant digit or the least significant bit. It's always a 0. It's only when you add and you start having carries that you propagate them over to the left. Now, this is very convenient for us because we can take the 1's complement of 8 by flipping the bits, right? We got 4 zeros, a 1, and 3 zeros. Now we got 4 1s, a 0, and 3 1s. That's the 1's complement of 8. Well, I can add 1 by turning the least significant bit carry on. I can add that extra 1 while I'm adding it to the -4. All right, so this eliminates a whole extra step. You don't need to calculate the entire 2's complement value by flipping the bits, adding 1, then adding it to -4. You just simply flip the bits and add it to the -4 and add the extra 1 all at the same time. That's the point here, okay? So this is I'm waving my hands all over in the studio here. This is a big deal, all right? Do all this at once. So what do we do? Here's my -4 plus 1's complement of -8 plus 1. 1 and 1 is 0 with a carry. You got a 0 with a carry, 1 with a carry, and that's 0 with a carry, 1 with a carry, 1 with a carry, 1 with a carry, 1 with a carry. And we talked about before, whenever we're adding things up, we throw away the extra stuff on the left, and we end up with the answer here, which is in fact -12 if you add up all the place values of these of the bits. Okay, it's as simple as that. Don't need to worry about subtracting when I can add and negate. Okay, done. I got a note to myself over here. It would be nice to show some more examples in what happens when you're doing signed and unsigned values. It turns out that when you're adding or subtracting rather unsigned numbers, you can still use the 2's complement method here. Even though they're unsigned, you can still do this and get the same answer. All right? Now, I'll leave that as a homework assignment, but this technique works no matter what. Notice I'm saying subtraction of binary numbers. You do this. Whether they're signed or not, this will work. Okay? Now, what happens when we get the wrong answer? Right? It should... come back here a second. What happens if I add two numbers that are gigantic together and there's not enough bits to hold them all, right? And I got bits flowing over to the left that I'm truncating, I can get the wrong answers. Okay? Let's take a closer look now at this truncation problem. All right? So we know how to subtract. But we need to now kind of think about truncation here. What really is going on? When you throw away the carry bit that comes out of the MSB, as I mentioned before, it is called truncation. All right, and we just throw them away and we ignore them right now. However, it could be that we could see a negative impact to the carry that flows into the most significant bit, or we're throwing the carries away when we really want to keep them when the numbers get too big or too small. All right, so let's look and see what's going on here. The examples above. Truncating the results, either A, had no impact on the calculated sums, right? Or they did, it was absolutely critical for that to happen, right? When we threw away the 1 bits, if we go back to the previous discussion, something like this, -4 plus a 5, if we don't throw this away, we get the wrong answer, okay? So truncating is important at times, okay? But we need to make sure it's always okay to do it, all right? So it either had no impact or it was necessary, as I just showed in the case of -4 plus 5. Okay, so let's then see at a couple of weird cases now. So far, everything's always worked. It's always fit. It's always been okay. What happens when it's not okay? If I take -8 and I want to subtract 1 from that, I mean, in my head, I know that should be -9, right? Well, it turns out in a 4-bit binary number, you cannot store -9. It's too large a negative value to store into these 4 bits using the 2's complement representation. It can't be done. So what happens? Well, if I want to subtract 1 from -8, and we already know how to subtract, so we take the 1's complement of the subtrahend, right? Then we add it to the 8, and we add an extra 1 using the carry into the least significant bit for the extra 1 that converts the 1's complement to the 2's complement, and so on. So we got 1 plus zeros is 1. That's a 1. That's a 1. 1 and 1 is 0 with a carry, and we throw the carry away, and we end up with this, which in binary is 7, okay? What we wanted was -9. Well, it turns out, in this case, if we keep this extra bit without throwing it away, if we don't truncate it, this thingy here is actually -9. Because that's -16 plus, 4 plus 2 plus 1 is, in fact, -9. So this is a case where truncation is actually wrecking it for us. On the other hand, the computer is always filled with a finite number of bits. And if I want to add a pair of 4-bit numbers and get a 4-bit result, what I'm really done is asked it to do something that's not possible. You can always come up with the value that you could add or subtract that always results in a number too big to be stored in the whatever number of bits you have. No matter what you do, you can always do that, right? You can always come up with a case that causes a bigger problem. That's what I'm talking about right down here. Therefore, let's take a closer look at figuring out how to determine when we have a problem, all right? We'll see that's called an overflow, all right? Truncation is merely the act of throwing away the extra stuff on the left when you have too much. Sometimes it's good. Here's a case when it's not so good. Other times, it doesn't matter at all. So how do we figure out when we really want to do it and when we don't want to do it? Okay, so let's look and see what's going on here. And, of course, I wanted to throw another example in here to suggest, look, it's not only a problem that occurs during subtraction. It's not only a problem that happens when you're dealing with signed and 2's complement values. It also happens with unsigned numbers, and it can happen with addition just the same, right? How, I want to calculate a value that's bigger than again, how many bits does it take to hold a number? I can always add 1 to that number and end up needing more bits or double it or something like that. You eventually run out of bits, and this again is this problem where the truncation, the mere truncation becomes a real problem that we call overflow. All right, so here's another example. What is this? I've got 14. This is an unsigned binary number representing 14. You know it's unsigned because this thing is a positive number there, okay? And then what is that? That's 8 plus 4 plus 2. That's 14, right? That's an addend. I want the other addend should be then a 3. I want to add 3 to 14. What is that? It should be 17. It would be nice to have 17, but I can't fit 17 into a 4-bit unsigned value. So if I truncate it, I'm going to end up getting 1. All right? If I use all these bits just like it did up there. It turns out that 16 would be the place value of this thing. And plus 1 is in fact 17. It would work again if I could somehow keep the extra bit. I could get the right answer. All right. So what is the conclusion here? Yeah, sometimes you gotta truncate a value. Sometimes you must not truncate the value. Sometimes it doesn't matter. All right. What do you need to do? Well, as I mentioned before, real computers are finite in size. And the only time that this truncation causes us a problem is when we try to put more data into a place than it can fit. So that's just broken as conceived. All right. So if we simply say, look, we'll take care of the cases when it does not matter, and we'll take care of the cases when we have to truncate. And in the cases where truncation causes us a problem because the numbers are too big to fit into the computer, that's the programmer's fault. Let them worry about it. Now, as long as we provide a way for a programmer to determine when something bad has happened, we can look the other way and say it's good enough. We've passed the buck. Let the programmer deal with it, okay? Now, this text that I've been working on is in the context of this thing called RISC-V, and the instruction set architecture definition uses these words unsigned overflow to represent the case that just happened right here when you're adding or subtracting two unsigned values and you end up with the wrong answer. That's the simplest way to put it, right? You end up with a sum that's bigger than you can store in the machine. They refer to that as unsigned overflow. And the situation where these carries and the truncation result in a problem when you're adding or subtracting signed numbers, they refer to that as signed overflow. And that's kind of a nice, simple way of remembering which kind of overflow you got. Does it apply to unsigned numbers or signed numbers? That's pretty straightforward. Now, there's a click here. This little 4 has got a footnote right here. And I observed that a lot of microprocessors, you go out there and read the doc for all kinds of other machines, quite often the documentation won't have unsigned overflow. They'll just simply say that is a carry condition, all right? Meaning that you have a carry out of the most significant bit. Okay, overflow on a machine like this is signed overflow. Just about every little microprocessor out there or a real CPU has this a set of flags or a way to determine whether you've ended up with an overflow condition of one kind or another after an addition or subtraction is the point here, okay? So they might use different names, but that's what all of this means. I'm going to use unsigned overflow and signed overflow in this course to refer to these two different situations. And I will use truncation to refer to the fact that we're throwing away the bit over here on the left. I can truncate without having signed overflow, as we saw before. Most of the time, with unsigned numbers, if I'm adding, I can never truncate a 1 and get the right answer. As we'll see, subtraction works a little different with unsigned values. All right, so let's look and see how this these other situations occur. How do I determine when bad things have happened is the point here, all right? So truncation may or may not be okay. When it's not okay, how do you figure out that it has happened? All right, so when you add two unsigned numbers, you can only get an overflow when there's a carry that comes out of the most significant bit that has resulted, therefore, in a sum that had to be truncated to fit into the allocated number of bits, and you ended up with something that was not, you ended up cutting the value off. You threw away the leftmost bit. Here's an example here, okay? What happens if I add 240 plus 17, and I'm using 8-bit addition? and I have an 8-bit sum. Well, 240 plus 17, these are decimal values, of course, and these are the binary, unsigned binary in this case, right? But I know this is unsigned because if this bit is set here and I tell you that it's 240, well, then clearly it cannot be a 2's complement signed value because this number here with this bit set on the left would have been a negative value. So this clearly is an unsigned number, and I'm adding this value down here to it. Now I would like to end up with what, 257, but I can't fit all that in 8 bits. So when I add these together, I got 1 with no carry, 0 and 0 and 0, and that's what 1 and 1 is 0 with the carry, 0 with the carry, 0 with the carry, 0 with the carry, and I'm truncating the extra carry away, and I end up with just this, which is 1, which is obviously wrong, right? I added 240 plus 17 and I got 1. That's a bit of a bummer, okay? Now, I note down here, sometimes we call this wraparound, right? Because what happens is if I keep adding numbers together, right? Let's say I started with 0 and I add 1 to 0 and I get 1. And then I add 1 to 1 and I get 2. Add 1 to 2 and I get 3. And I'm using an 8-bit unsigned value to hold this thing. Well, I can count all the way up to 255 using these 8 bits. When I add 1, when all these bits are on, the value, when there's 8 bits, if they're all 1s, that would be 255. And when I add 1 to that, I end up with a situation where there's a carry coming out of the left, like a lot like this, and I end up with 0. And we say it wraps around back to 0. So it counts up and up and up and up and up, just like this. It's counting 240. We're getting bigger and bigger and bigger, and all of a sudden it goes all the way back down to 0 and then comes back from the other side on the number line, so to speak. So we say that this is a wraparound, all right? Now, in this blue box down here, I summarize. When you are adding, unsigned overflow occurs whenever there's a carry that comes out of the most significant bit, period. When adding, unsigned overflow. So for unsigned addition, you get overflow if you get a carry that comes out of here. It's as simple as that, right? Now let's look and see what happens when you subtract unsigned numbers. As I said earlier, you can use this even though the numbers are unsigned. Another beautiful thing about 2's complement and the way we're doing our addition and the way we represent these values, you can actually temporarily use the same technique where you flip the bits and adds 1. You can actually treat this as a 2's complement, the subtrahend as a 2's complement number temporarily, even though I'm doing using these values as unsigned numbers. This will always work, okay? That's another huge positive takeaway of this particular encoding scheme. So if I really wanted to say, give me the value of 3 minus 4, and this is an unsigned binary number, and this is an unsigned binary number, I can still take the 2's complement of 4 and add them. And I can then get the right answer. So if I want to say 3 minus 4, what do we got here? There's my 3. There's the 1's complement of 4. And I set the least significant bit carry over here. And now I can just add them together. 1 and 1 and 1 is 1 with a carry. That's 1 with a carry. That's 1 plus 0, 0 is obviously 1 with no carry. And 1 and 1 and 1 and 1 and 1. And I get no carry out at all. Okay, what do I get here? Well, these 8 bits, again, remember, this is an unsigned addition. I ended up with 255. Well, what should I have got? What's 3 minus 4? I should have ended up with negative 1. Well, if these are unsigned numbers, I can't have a negative value. So it makes perfect sense that if the difference after a subtraction is gone, or if it's supposed to be a negative value, I can't possibly represent that. So no matter what, I'm going to end up in a weird situation. All right, so that should make sense, okay? But our game that we played up here, oh, look, whenever I add 2 unsigned numbers together, if and only if there's a carry that comes out of the most significant bit, there has been an overflow, okay? That's a nice simple rule. Well, dang it, it doesn't work down here because I had a 0 that came out over here, and it's wrong, okay? It turns out that when you use this specific technique to perform a subtraction, by abusing this sense of, I'm going to use the 2's complement of 4. And I'm going to play this game where I take the 1's complement and set the LSB carry, and I'm going to add them in order to perform a subtraction. It works fine, except the meaning of this carry is the opposite. So the rule here then is when subtracting unsigned binary numbers, unsigned overflow occurs when there is not a carry coming out of the most significant bit. All right. And again, in parentheses, I say this is true if and only if you use the carry in technique that I did right here, where you set this to add the extra 1 during the calculations of the 2's complement value of the 4 when you're adding it to the 3. You have to do all this at once in order for this statement here to be true. There are cases, I'll leave that as a task for the viewer and reader, as perhaps a homework assignment, to come up with and show the cases where if I don't use this technique and I flip the bits and add 1 to calculate the 2's complement of the 4 and then add that value to the 3 without this thing being set here, there are cases where this technique will not work correctly. So this isn't necessary evil. Well, it's very convenient, actually. It's not even, this is a gift that you can use this technique. It's just that when you're using this technique to subtract, a 0 means there's a problem when you have an unsigned number. And when you're adding, a 1 means you got a problem. All right? It's as simple as that. Where signed numbers are concerned, we have a kind of a more interesting situation here. If you add 2 signed numbers, an overflow can only occur when the 2 addends are positive and the sum is negative, right? When you add 2 positive numbers, if you get a negative number, you got a problem. Or if the 2 addends are both negative and you end up with a positive sum, you've got a problem. All right. So, logically, again, it's sort of like the unsigned case where, you add 2 numbers and you get a crazy result that's either too big or too small. Same thing. It's really saying the same thing here, but you can use the sign now to kind of determine whether you got a problem, right? 2 positive numbers added together, you can never get a negative value. But if you overflow, it turns out you end up with a negative value. And the same thing if you add 2 negative values together and you end up with a positive one. Okay. When subtracting unsigned numbers, an overflow can only occur when the minuend is positive and the subtrahend is negative and the difference is negative. What does that mean, right? Well, think about that, right? Minuend is negative. That's the number I like to think of as the number on the top when you write it out longhand, okay? So the minuend is positive and you're subtracting a negative subtrahend from that value, right? And remember, we're going to flip the bits and add 1 and change the sign of the subtrahend, and then we're going to add using the technique we're talking about here, right? So therefore, that really means that what we're doing in this subtraction is we're doing an addition of 2 positive values ultimately, right? And if you end up with a negative difference, you got a problem, right? And the same thing is true the other way around. If the minuend is negative and the subtrahend is positive, and you want to subtract them, what you're really doing is you got a negative number, and you're subtracting a positive number, so it needs to go further negative in that scenario. If you end up with a positive value after all that, you've gone the wrong, it's wrapped around again and ended up in the wrong place. So let's look at some examples. Maybe this will help make more sense. So what do we got here? If we want to add 2 signed numbers, now we're just dealing with signed numbers, and we look closely at the carry values, all right? So we're adding, right? This is an addition operation. So we're not playing any games. We just got, let's add 64 plus 64. It would be nice if the sum was 128, but in reality, it turns out in this example, it does not, right? So what do we got? All these are 0, 0, 0, 0, 0. Finally, we end up with 1 plus 1 is 0 with a carry. So a carry just went from this place here to the most significant bit, right? And that carry caused the sign to flip in this number, so to speak, right? So you add these two numbers. This is a positive value because this is a 0. This is a positive value because that's a 0. And you've added them together and you ended up with a negative value. No matter what this is, it's wrong, right? So the carry that came out of there, of course, is a 0. So you can't even play a game that says, oh, look, if the carry that came out of there is 1, it's broken, like we can in the unsigned case, right? So this is kind of a weird situation. So let's look look closely at what's going on here and trying to figure out this rule. All right. Turns out there is a simple rule, and we can take advantage of it. Now, as I point out here, granted, if we had more bits in these numbers, we could store the sum and it would work and it would have been okay. But again, you end up with a problem where there's always going to be a case where you can always choose a number that's so big that it overflows into the leftmost bit. It's as simple as that. So no matter what, this problem can always occur. It'll just happen with a bigger number. That's all. So this always occurs. We need to be able to identify it. So let's look and see what happens when we have the two negative values and see what happens there. So we had negative 128 plus negative 128. All these are zeros. We end up with a 1 and 1 and a 0 with a carry over here, and we end up with a sum of 0, which is kind of weird because this should be what? Negative 256 should be the sum of these two things, and we ended up with 0. So we got the wrong sign and the wrong magnitude. So that's a drag. And in this particular scenario, we had a carry out of the far left of a 1. So we had a 0 there, and it was wrong. We have a 1 here, and that was wrong. So this should give us a clue that just looking at the carry that gets truncated out of these is not really the answer. So it's not really the problem, right? So let's look at, what do we got? Figures 2627 and figure 27 demonstrates the importance of discarding the carry. Where were those figures at? Here's figure 25. Oh, these are the guys down here, 26 and 27 right below. Good. That's handy. I can't stand it when the figure ends up on 9 pages away, Don't you hate that? Okay, so what do we got? Figure 27 demonstrates the importance of discarding the carry from the sum of the MSBs of signed numbers when the addends do not have the same sign. Yes, of course. And what is this one doing? So we got negative 3 plus a negative 5. We should end up with a negative 8. And we do. Right? We're adding. So we're not playing any games down here. We're not doing ones, complements, or anything else. We're just adding still right now. Same with this guy over here. No special games. Negative 2 plus 10 should be some positive number. Should be positive 8. And that is positive 8, right? Because the place value of that's 8 and everything else is 0. This one here is negative 8. You can go ahead and add them all up yourself. There's negative 128 plus 64 plus 32 plus 16 plus 8. Plus 0 plus 0 plus 0 should give you negative 8. And you can obviously see we got a carry out of 1 here and a carry out of 1 there. So what do we got here? We can also wrap around after successive additions. And in the case of a signed number, you don't wrap around to 0, by the way. So this little paragraph discussion here is about the fact that you don't go from like this massive positive number and then you go back down to 0. Okay, it won't go from the maximum value back to 0 in the signed case. All right, the signed case instead will go from what we will call the most positive value that you could ever have, and it'll wrap around to the most negative value. And we demonstrate that here in figure 2.8. What do we got going on here? So the most positive value you could ever have is set every one of the place value bits to 1 except for the negative 1, right? That's the only one that could contribute a negative value to the number. So if I take the most positive number and I add 1 to that thing, what happens? Well, 1 and 1 is 0, the carry, 0, the carry, 0, the carry, da-da-da-da. Eventually we end up with a 1 over here followed by all zeros, which is, by definition, the biggest negative value I could ever have. We know that the carry that came out of here that's truncated was 0. And the value of our sum, if we add 1 to 127, is negative 128. So what do we know about all this? This is the rule down here. You get a signed overflow whenever the carry that goes into the most significant bit is not the same as the carry that comes out of the most significant bit. All right, so now we got to go back here and let's look at all these things, right? Look at the ones that didn't work. Here's one that did not work. Well, what was the carry that went into the most significant bit? Well, from this column here, this is the second most significant bit, right? Whatever the carry is here, this one was a 1. We add these up, we get 1, and the carry that came out is a 0. So the definition of overflow with signed addition is when these two values are not the same. The carry into the MSB is not equal to the carry out of the MSB. Period. That's what happens when you have a problem when you're adding two signed binary numbers. So it's almost as simple as the unsigned case. But you need to compare these two guys, right? And that is the special case of the XOR function, as we mentioned before. If you just simply take the XOR of these two bits, whenever that's true, you know you had a signed overflow, all right? And as we will see when we start looking at the Boolean algebra and what it means to add up numeric values, there will be an XOR function that says, hey, when that's true, there's been an overflow. And that's how the CPU determines after an addition operation takes place on a signed operation. That's what will dictate whether or not it is flagged, whether an overflow takes place. So let's see what happened here. There's a 0 going into the carry and a 1 coming out. It's the opposite of what we just saw before. And we added these two values and we got the wrong thing again. So these are different. Therefore, yes, we have a problem. Let's look at this one. When I said -3 plus -5 and I got a -8, which is the right answer, the carry that went into the MSB from here over to there is a 1, and what came out of the MSB is also a 1. These two are the same, therefore there was no overflow. Here's another situation. -2 plus 10 equals 8. You add them all together. The carry that goes from this column here, 1 and 1 is 0 with a carry right there, 1 and 1 is 0 with a carry here. These two carry values are the same. Therefore, there was no overflow that took place. Here's another one that fails. 127 plus 1 should be 128, but in reality, we ended up with -128. Well, look what happened. Blah, 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 blah. The carry that went into the MSB is a 1. The carry that came out is a 0. So in here, this is what happens when you have a overflow from adding signed binary numbers. And I can see that I need to revise these notes because I don't give you examples of what happens when you subtract two signed binary numbers. But it turns out when subtracting, you end up with the exact same situation. So I will say, I'll leave that as a task to the viewer to go home and work out some scenarios with subtraction to prove that the same rule holds true when you're subtracting two binary numbers using the flip the bits and add one technique, as well as when you're just adding two signed binary numbers. This rule is in fact true. All right. I will leave the sign in 0 extension as a reading assignment for the student. Turns out these are pretty straightforward. What does it mean to make a number that has more bits than it does right now? I have an example like a 20-bit number, but I want a 32-bit number. How do you convert a number to a number with more bits in it? All right, so there's a couple of little diagrams down here. I suggest you go ahead and read this and convince yourself that it is either true or there's a typographic error in here, and let me know so I can fix it. All right, so thanks a lot for watching. I'll see you next time. Bye.